All right, recording is rolling. It's Thursday, January 12th. I've got a couple demos lined up for you guys, and then we're going to take a lot of class to look at these textbook puzzles. So let's switch the screen over here. All right. All right, so you guys remember learning about constructive, destructive interference and standing waves. I just did a demo before I started the recording. Set up a standing wave with the transverse wave with the slinky. All right, so here, let's check this out.
My name's Chase and I live in California, and I'm gonna try to break this wine glass by only my voice.
This is called resonance. And a lot of structures will have some associated resonant frequency. Like if you hit the certain frequency, which you happen to be hitting the right pitch, and just like amplify that that energy to it just over and over. So, like if you know like the top diameter, like the diameter and circumference of the top of the glass, there'd be an associated wavelength that could set up, right? And if you set up a standing wave around the circumference of that glass, right, you just keep pumping in the same frequency over and over. Right? Now, what's sort of related to, wait, I gotta pause before I play this. Okay. How many guys are in ROTC? ROTC. Right. You guys ever march and step left, right, left, right? Okay. But you might know there is one place where troops are specifically told do not march and step, and that's over a what? Bridge. Over bridge. And why would that be? Yeah, because if you hit the resonant frequency of that bridge, that structure, same thing as that wine glass. You guys want to see that happen? Well, not exactly with marching troops, although
as you can see.
Here, let me mute this guy. Okay, let's go back to 1940. So, in the Great Depression, route in Tacoma Narrows on the west coast is Washington State. Right. So this bridge opens. Now, for the first few weeks, it would kind of bounce up and down. It wasn't really supposed to, but they saw it didn't. The engineers were checking it. Say, okay, well, we don't really see any cracks or form or anything, so we'll just keep an eye on it. But then one day, it goes into this type motion. There's a. Let me ask you guys, where do you think the energy is coming from to make it do that? Because it's not just doing spontaneously. Wind. Yeah, wind. Yeah. So there's this crosswind, right? I think the time period of this is like 5 seconds or something. You guys can see a car out there. There's an engineer walking along this nodal line. Right? I think it's about 5 seconds. Because if the time period's about 5 seconds, what's the frequency in hertz? Well, yeah, 1/5 of a hertz, right? Because time period and frequency are just reciprocals of each other. There, yeah, you can see walking across there. Yeah, so he's checking this out. He ended up being all right before this thing broke apart. Oh, guys, what is that bridge made out of? Concrete and steel? Yeah, concrete and steel, right? Well, it doesn't last forever. Eleven 10 a.m. Yeah, then this happens. The guy was able to get off himself before that collapse. So
where was this?
Tacoma Narrows. It's in Washington State. Oh. Yeah. Now, what engineers actually did is they went back and just rebuilt the bridge because like these columns here are fine, right? There's nothing wrong with those. Right? They went back and just rebuilt the bridge, and they just made one tiny change to prevent all that from happening. Of course, there's some good engineering knowledge that came out of this, right? What not to do. Let's see if I find a good shot. Okay, kind of hard to tell. But switch my screen back over here. what they ended up doing was, instead of using we got a cross section here. So the way they originally built this is they, okay, well, we've got a bunch of cars going across, right? Cars have a lot of weight, it's pushing straight down. We gotta have something that carries the weight. Okay. So they had this vertical girder structure going across all these vertical girders, okay, which would be good at handling a bunch of vertical stresses. Okay. But the real world, of course, there's a bunch of other variables going on, like vibrations and crosswinds and the forces from all different angles. Okay. So this is really good at handling vertical forces, but only vertical forces. Okay. So anything else, it's not right. So has looked like a resonant frequency of about 0.2 hertz. You guys were saying. Okay. What do you guys think they did to go fix this? They changed it from a girder structure, vertical girders, to what? Truss. Truss structure. Yeah. You just go in, throw some truss structure like this. Right. Here's one type truss structure, right? Now you got all these little triangles, right? So now you've got parts that can carry like horizontal loads also. Yeah, so that's a much safer setup right there to have like a truss structure, right? Okay. Oh, that reminds me a lot of unit 2 in this class. You guys think you could like pick a point like here and all the forces should sum to 0, right? Maybe there's like compression in the top. Maybe if you get down here, like 1 in the bottom, maybe it's like tension in the bottom. Okay, see this bridge kind of like starting to wants to bend this way, right? Tension at the bottom, compression in the top, probably. Well, I mean, overgeneralizing a little bit, but guys. Okay, so yeah, there's a whole class you can take if you're going to be an engineer. It's called statics. You take in college, where you just do a lot of analysis like this. With a truss system, you pick a point, say the forces have to sum to 0 along each axis, and then you can figure out what's the compression and the tension along each one of those bits. All right, so there's a little bit of extra info. Let's take some time to look at these puzzles, chapter 13 puzzles. All right, so really what I want to do is maybe give you guys some pointers on how to think about these, give you guys the opportunity to solve some of these. Get you guys a little bit head start here. So number 12, this is conceptual question number 12. Grandfather clock depends on the period of the pendulum to keep correct time. Right? So you guys know grandfather clock, right? So got right, so we got this pendulum, like swing back and forth, swing. Okay. Now in this class, usually they'll say like the string is negligible mass or something, which might not be exactly true here, but you guys get the idea. Suppose the clock is calibrated correctly. So 1 second is 1 second. Okay. And then the temperature in the room increases. The temperature goes up. Okay. Does the clock now run fast or slow? Let's narrow it down to those two. It's going to run fast or slow now that the temperature in the room has gone up. Okay. And this has to do with materials. They gave you guys a really big hint here. Right? Like you have to get this. A material usually expands when the temperature increases. Okay. Most materials expand when the temperature increases. There's a couple exceptions, but like metals will expand when. While you guys are thinking about that, I'll give you guys a little bit more details. Suppose you have like a metal rod, and it's some length. I can say L. I'm going to say L naught, like an original length, L naught. Okay. And then the temperature goes up. If the temperature goes up, you think it's going to expand? Okay. And maybe it'll expand in all 3 dimensions, but if it's a really long object, we mostly care about how much it expands this way, right? Okay. Maybe a tiny bit. The other directions too. I'll call this delta L, right? The change in length, right? So it was this long, and then you heat it up and it expands a little bit. Okay? And I can tell you what that increase in length is. Okay? So engineering materials concept. Okay? It's the original length times the coefficient of thermal expansion times the change in the temperature, right? So original length, change in temperature, and this is a coefficient of thermal expansion. I know we use alpha for other things too, right? Coefficient of thermal expansion. Okay. So just to add to your guys' knowledge a little bit. Okay. All right. So now you guys been thinking about this a little bit. I want to see show hands. Show hands. Is this clock now going to speed up or slow down because the temperature in the room went up? Okay. How many guys are thinking, that clock's going to speed up? It's going to speed up. Who says that? Who says slow down? Slow down. Oh, yeah, you guys are right. It totally is going to slow down, right? Right, so good call, good call. Because the fact that it gets longer means that increase, right? If that increases, then the time to swing back and forth also increases, which means it takes more time to swing back and forth, so the clock runs slow. Okay, you guys got that. All right, nice. Block mass 0.6 kilograms attached to a spring with a force constant of 130 newtons per meter. Ooh, yesterday you guys were figuring out spring constant of the springs that you're working on. Oh, after you guys left, I looked back at the table real close. I missed a detail that I actually I got on one half lab, I had it in newtons per meter, and the other half I put newtons per centimeter. So I don't know why I did that. I need to change that for next year, but oops. But once you adjust for that, like if you multiply one of them by a factor of 100, they should have been pretty close to each other, right? The two numbers for your lab yesterday. I'll get those lab grades in sometime soon because the second semester actually starts today. Block is released from rest at the instant the spring is stretched. An amplitude of 0.13 meters. You call that x equals 0.13 meters, right? They're using capital A for amplitude, like the maximum stretch amount. At that instant, find the force on the block and its acceleration. Right. So what formula are you guys going to use to solve for the force? F equals kx. That's just back to Hooke's law. That's Hooke's law, right? F equals kx, right? Here's your k. Here's your x, right? So you get the force, right? What would have been trickier is if they just prompted you to only solve for acceleration, because how are you going to get acceleration? Well, you have to get the force first, right? And once you know the force, Hooke's law, how do you get acceleration? Yeah, Newton's second law of motion, right? F equals ma. Oh, there's the mass. Boom. Right, you guys see how it's all going to pop together? Okay. All right. Number 2, spring oriented vertically attached to a horizontal surface. Got a spring constant of 1.46 kilonewtons per meter. Ooh. Can you guys take that number and multiply by a factor of what to get to newtons per meter? 1,000, right? Okay, so is that 1,460 newton per meter? Okay. How much is the spring compressed? We got data object, that mass, 2.3 kilograms, placed on top of the spring and systems at rest. Oh, okay. Are you guys going to use what, conservation of energy or Hooke's law with forces to solve for that one? It's just sitting at rest. I'm thinking Hooke's law, just F equals kx, right? So you got mg is the force down and kx is the force up, right? And they need to balance out, they need to zero out, right? So yesterday, you guys remember with the oscillating springs, you attach a mass and then let it hang down. Okay. It's like, well, how far is it pulled? Well, there were two different stretches. Because there was coming out of the lab around here. Here we go. Okay, so you hook on a mass right here, let it fall. Right, there's an x max, and then it oscillates back and forth a little bit, and then it reaches x equilibrium. Okay, so the problem we were just looking at from the textbook is kind of like this one on the right. Right, so there's a force up, there's a force down, they balance out. Okay. But the maximal stretch value, you have to use conservation of energy, right? There's all gravitational potential here, there's all spring potential here. Okay. And that's in your notes from yesterday too, because I walked you guys through that one yesterday. A spring 1.5 meters long with a spring constant of 475 newton per meter from ceiling. Oh, and an elevator. Ooh, it's about to get a bit more interesting. Block mass 10 kilograms attached to the bottom of the spring. By how much is the spring stretched when the block is slowly lowered to its equilibrium point? Slowly lowered to its equilibrium point. You guys think that's the scenario right here? Slowly lowered to its equilibrium point. Right. You guys going to use dynamics, right? The weight down and the spring force up. You need to balance out. You need to zero out. Right. I think so, right? Okay. If the elevator subsequently accelerates upward at 2 meters per second squared, what is the position of the block? Notice they're saying position, like an exact position, right? So specify this, like this location. Taking equilibrium position found part A is y equals 0. Okay, so if it's just in regular gravity, it's just at 0.0. Okay. And then now we're going to accelerate this elevator upwards. Okay. And up is in the positive y direction. Okay. So let's get a picture going here. Right, so we got this hanging in an elevator, okay, and then the elevator starts accelerating upward. Okay. What does it feel like inside that elevator? Do you feel really heavy or really light? Really heavy, right? Because that floor is being actively pushed into you. If you're staying on a scale, your weight reading would go up, wouldn't it? Right? Your apparent weight. So is this spring gonna like retract or is it gonna expand? Yeah, I think it's gonna expand more, right? Because now this weight feels super heavy, right? So do you think it's position like if this is position 0 right here, right? If you read the text, they said this is position 0, right? And they said up is positive. Is it gonna go into some negative territory? It's going to. The answer would be negative, right? Whatever that is. Right. Oh, you guys remember elevator physics? Let's review that. This is from there's some a lot of crossover content with stuff from last semester on this one. Okay. Complete this problem. Oh, all right. Here, pop quiz with you guys. Can you guys derive the apparent weight in an elevator equation from scratch? Can you guys do that? Set up a free body diagram. Figure out what is the force rating in an elevator that's accelerating. So if an elevator is accelerating up or down, if you know what you're doing, go ahead. You need some extra hints. Think about this. So here's some extra hints. Suppose you're standing on a scale, you get your weight, right? And then the elevator starts accelerating. Maybe it's accelerating up, maybe it's accelerating down. Let's have it accelerating up, just like the book problem. Can you guys draw a free body diagram for that guy? And then derive how do you get the reading from the scale, right? Based on the acceleration. Okay, give you guys a little bit of head start here. It should totally be a skill that you guys have. All right. Okay, so everybody at least has this, right? On their notes in front of you guys. You guys drew the weight down and the normal force reading from the scale up. Okay. Or if it's maybe you said tension in an elevator cable, I'll just call it normal force from the scale, right? And you guys drew this is greater than this because it's accelerating up, right? Okay. Okay. So you got that. What's the next thing you guys did? If we got forces and accelerations involved, that sounds opportune for what? Newton's second law of motion, right? All right, now I could say F equals ma, right? But I got two different forces here. This F refers to what? Net, net force, the net force. Boom, right? Okay. And what is the net force? The difference between those two, right? The difference, right? So we got the normal force up minus the weight down. It's going to result in mass times acceleration, right? And then if you want to solve for the reading on the scale, well, I should have asked you guys, but that's what that would be, right? The reading on the scale, right? Or tension in elevator cable, it's the same math. Right? So can you guys take this and add it over? And the rest is just algebra, right? Mg plus Ma, right? And if you like, you can factor out the mass of the guy, it's the same mass, right? Right. That should look super familiar. You guys have seen this several times the first semester. Okay. And then be sure you can derive this from scratch exactly like you're seeing it, because there's a good chance this could totally pop up in an FRQ, and they would want you to, there could be like point. That could be like 3 or 4 points right there. What if it's accelerating down? Be a little bit different, but what would be the only difference in this final outcome? Yeah, this would be G minus A is accelerating down. Okay. What if he's in pure free fall? Okay. That A would be G downward, right? G minus G would be 0. The scale reading would be 0. Right? Feel like an astronaut. All right. Get stuff to check going on. What else we got? If the elevator cable snaps during the acceleration, describe the subsequent motion of the block relative to the freely falling elevator, and what is the amplitude of its motion? Well, we just talked about that, right? So if the elevator cable snaps, then everybody's gonna feel like an astronaut on the inside, right? Everyone's just floating around, right? So let's break out. I'm missing something here. Okay, next one, number 8, block mass, 2 kilograms, attached to spring with force constant of, ooh, look, scientific notation. Is that called 500 Newton per meter right there? Lies on horizontal friction on the surface. Oh, right, that's a really common scenario. Right? I bet you guys are gonna see that in your AP classroom when you haven't started that yet. We're gonna cover AP classroom on Tuesday. The block is pulled to position of 5 centimeters to the right of equilibrium, released from rest. Find the work to stretch the spring and the speed of the block as it passes through the equilibrium point. Right. And so one thing at a time here. I'm gonna have you guys solve this. Let's solve this one. I want you guys to solve it first, okay, and then make sure you get the right answer. So part A, the work to stretch the spring. Everybody, go ahead and solve that right now. The work to stretch the spring. Let's see how many guys are gonna get this right. So we got 500 Newton per meter on the spring constant. We got 5 centimeters of stretch. Pull back 5 centimeters. All right, who figured out how much work did it take to stretch that? Who figured it out? You guys still working on it? I got like all right, anybody got the answer? Yeah, what's your score?
Is it 12,500?
I think that's something smaller than that. Guys, work. What's oh yeah. Okay. Okay, true. 4 times distance. Work is 4 times distance. Now here's the tricky thing about stretching a spring. As you stretch it more and more, does it require more and more force? It does because F equals kx, right? So force is not actually constant, right? Like you could solve for the force at the point that you pulled it 5 centimeters, right? That might help frame the problem, but okay, but it's a variable force, like it builds up to that point. How about this? The work that you do stretching it. Suppose you stretch it and you're holding it at rest. Where did all that energy go? All the energy is now in the spring. And what's the formula for energy in a spring?
1/2 squared.
1/2 kx squared. That's what everybody was thinking, right? 1/2 kx squared, right? So the force to stretch it is F equals kx. That's Hooke's law. The energy now that took to stretch it, now stored in the spring, that's 1/2 kx squared. All right. So anyway, you run those numbers. I got something that looks about like that. Okay. Let's do the graph version of this too. Graph, because suppose they have force in newtons versus stretch amount in meters. Right. We're going up to 0.05 meters. Right. And it took well, we know the spring constant's 500 Newton per meter. That's what they told us. Okay. Guys, what's this graph going to look like? Can you guys draw that graph before I do? For stretching, mass attached to a spring, or stretching the spring. Okay. Did everybody just right now draw that in their notes? That's what you guys just drew, right? Okay. Yeah, the fact that it's a linear relationship, that's what Hooke's law says. Isn't that F equals kx? Here's what they told us. They said K is 500 Newton per meter. Okay. Now, if F is equal to kx, notice it's not a constant force, right? But like there's a maximum force to pull it, right? What property of this graph also could tell you the energy that it took to pull it, the work it took to pull it? Yeah, the integral, let's say the area under the graph, that's the area of this triangle. That's how much work it took, right? Because force times distance is work. Newtons times meters, that's some number of joules, but it's a variable force. So gotta take the area out of that. Right? Let's see if that gives us the same answer. Right? I can figure out what this maximum force is. K times X, that's 25 newtons. So if you pull 25 newtons, pull up that one. Right? So it's a variable force. Okay. Then isn't the area of a triangle 1/2 base height? 1/2 times base times height. Oh, look, it's the same thing. It's the same thing you get with 1/2 kx squared. There's two different ways to do it. Here's the like strictly algebraic way to do it, and here's the graphical approach. Boom, boom, same thing. There's a part B on this. What's the speed of the block as it passes through equilibrium? Most important thing I think with that question is, do you know the framework that you would use to solve that? How are you gonna figure out what's the maximum speed going through the equilibrium point? Boom! Conservation of energy. Conservation of energy. Right? Because at the point that he's holding it right here, and actually you know exactly how much energy is in the system, it's like this many joules. Right? More generally just say 1/2 kx squared or spring energy, right? Energy spring. Then you let it go. Now, as it's going through the equilibrium point, where is the energy? Well, there's no energy at height because there's no height change. Is there any energy stored in the spring at the equilibrium point? No, not at the equilibrium point because it's not stretched at all. 1/2 kx squared, x is 0. So no energy there. So where's all the energy? Kinetic, yeah, in the motion. So here's your framework. And there's the setup, right? That turns into that. And then you know everything except for V, you can solve for V, right? See that? Hey, how about this? How about this? Here could be a good proportional type question from AP. They said you pull it back like 5 centimeters, right? What if instead you pull it 15 centimeters? That's 3 times the stretch distance. 3 times the stretch distance, what's going to happen to the maximum speed if it's going through the equilibrium point? If it's 3 times the stretch amount, what's the maximum speed?
3 times.
Also 3 times. Because they're both squared, right? Okay, so factor 3 squared, right? Yeah, so if you pull it back 3 times, it's also 3 times the speed. Okay. What if you had a spring that was 9 times the stiffness? 9 times the stiffness. How many times the maximum speed would it be? 3. Yeah, 3, right? Because 3 squared is 9. B match, right? Okay. What if you had a block that was 9 times the mass? Has more massive, is that going to speed it up or slow it down? Going to slow it way down, right? Because it's so much more inertia. So 9 times the mass is going to translate to what times the maximum speed? A third. Because isn't a third squared times 9? That's a wash. It's the same energy, right? So 9 times the mass, a third times the original speed squared, it's the same energy. All right, it's gonna be a pretty good review. Number 11. Child's toy consists of a piece of plastic attached to a spring. Spring is compressed against the floor distance of 2 centimeters. I might call that 0.02 meters. Toy is released. The toy has a mass of 100 grams. How many kilograms is that? 0.1. Saves my example yesterday, right? 0.1 kilograms right there. And rises to maximum height of 60 centimeters. How many meters is that? 0.6. 0.6 meters. Okay. Estimate the force constant of the spring. Okay. I tell you, one of the simplifying assumptions here is going to be that the spring itself is approximately massless. And if you were thinking something to do with collision physics, you wouldn't be completely wrong. But they never do collision physics with us, so don't do anything with like momentum. Okay. All right. So, what framework are you going to use to solve this? Energy, conservation of energy. Right. And where was all the energy initially? In the spring. Compress this down 1/2 kx squared. That's energy in the spring. Then release it. It's going to fly to some maximum height. At the point of maximum height, it's all what kind of energy? Gravitational potential, right? You guys go from 1/2 kx squared to MGH. Okay, figure out from next. Alright, 19. I'll tell you guys what, 19, long story. This one is didn't make it to the solutions. Oops. So we'll do it in class right now. 19. Make sure everybody gets this one. Outdoor market, bunch of bananas attached to the bottom of a vertical spring with a spring constant of 16 Newton per meter set into an oscillatory motion with an amplitude of 20 centimeters. It's observed that the maximum speed of the bananas is 40 centimeters per second. What is the weight of the banana in newtons? So let's translate these numbers to base SI units and then figure it out from there. So 19. Okay. Got a bunch of bananas. Spring. Okay. And we're gonna pull this down and let it go. Let's go. Wow, 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 wow. Kind of like your lab yesterday, right? And so what numbers do we have? We got K is yeah, thanks. 16 Newton per meter. It said your textbook always gives 3 significant digits, but I'll just call it 16. Amplitude of 20 centimeters. So if this is the equilibrium position, then it can go. Each of those is the amplitude in compression, amplitude in tension. Right, this could be 0.20 meters. Right, that's what 20 centimeters is. And the maximum speed of the bananas is 40 centimeters per second. So when it's going through the equilibrium point, that'll be the fastest it's going. It's got a speed of, well, I'll call it 0.40 meters per second. What is the weight of the bananas in newtons? Okay. I'm thinking we should probably solve for the mass first and then worry about weight after the fact. Okay, I think we do that. Okay. Let's think about this one. So give you guys a little bit of time to solve that. You guys solve it. I'll solve it off screen. See what we come up with. Anybody got some good progress on this? All right, tell you guys what, I thought I knew how to solve this and I realized I don't immediately right now. So we'll come back to this one probably tomorrow. We're gonna come back to this one. Be my homework tonight. All right, 34. Man enters a tall tower needing to know its height. He notes that a long pendulum extends from the ceiling to almost the floor, and its time period is 15.5 seconds. How tall is the tower? Okay, yeah, let's start with that. How tall is the tower? Okay. So I'll solve it. You guys solve it. All right, who figured it out? Yeah, what you got?
59.6.
All right, glad you got it. 59.6 meters. Sounds right. 59.6 meters. All right, so did you guys start from this oscillation formula right here? Okay. Now, your college physics textbooks questions tend to be more kind of like this, like okay, you have a formula and then solve for something. You get to AP more like proportional questions or graphing questions, and just something to look for. What you guys doing? AP classroom this weekend too. Right? Okay. This is actually, if you ever see a Foucault pendulum, some universities have these at some science museums. They might be like several stories tall, so you can watch this thing swing back and forth. It takes a long time. It might take 15 seconds, and then you can calculate what's the height of the building, like how high is that shaft. Right. So here is solving in terms of algebra. Right. You can get the length of the pendulum in terms of all these other things. Right. You guys should be really comfortable at this point in the year with like doing this algebra process, right, in terms of variables. Right. You guys can definitely do that, right? Solve in terms of variables. Okay. Now your guys' textbook solutions here. Looks like feel a little bit different. So like that. All right. So there you go. Yeah. That's all. Part B, if the pendulum is taken to the moon, where the free fall gravity is 1.67 meters per second squared, what is the time period there? Right. Well, now that you know what the length is, which is the answer to part A, can you just go back to the original formula, like straight from the paper, straight out of the book, right? Because you would have solved for this. Now we got moon gravity, solve that. Part 2, object attached to a spring vibrates with simple harmonic motion. It's described in this figure. Oh, Haley, that looks like those oscillation graphs that take you guys through. Send your notes. For this motion, find okay, all these different properties. Okay. Let's start with the amplitude. What is the amplitude for this motion?
4.
Here, just that right there. Yeah. Just 2 centimeters. 2 centimeters. That's it. There's your amplitude. What is the time period? Yeah, time period is 4 seconds, right? I see 4 seconds from there to there. It's like one full S shape, one complete oscillation. What is the now angular frequency? I think I told you guys about briefly. This is like if you're trying to construct a formula, it's good to get angular frequency. And I was using the Greek letter omega with this. Right? Remember I was telling you guys it's 2 pi times just the regular frequency. And what is regular frequency? How can you get that very quickly from the graph? Frequency is 1 over the time period, right? 1 over the time period. Right. So angular frequency. So this, remember, this is angular frequency, right? Is 2 pi times then 1 over the time period, right? And the time period is 4 seconds. It takes 4 seconds to oscillate back and forth once. Okay, let's pop some numbers in there. Get that. What is the maximum speed? Maximum speed. Okay. So, okay. But it's going to be related to this. If remember, I told you guys if x is equal to a times sine omega t, right? Okay. That velocity is equal to how's this formula going to go? A times omega times cosine of omega t, right? Remember, omega is the angular frequency, so it's going to feed in there. Okay. And then, okay. Yeah. Now, if you're playing off this amplitude, that would specifically tell you maximum speed, right? Because the speed's always changing, just like the location's always changing. But look for maximum. The maximum acceleration. All right. Well, you can just head on down these formulas that we go through it for oscillation. Pull this up. So we're kind of back to this, right? Right. So maximum acceleration, you can use something like this, right? Right, so sine and cosine just oscillate. Rate change cosine, it's like a negative value. Okay. And every time you do another rate change, you pull out another angular frequency. Okay. It's kind of the advantage of calculating angular frequency for this type of stuff. Okay.
In those equations, the omega is the angular frequency.
Yeah, omega is angular frequency, not angular velocity. I know we were using it for last December, but okay, so angular frequency. Yeah. Equation for position as a sine function. Okay, well, let's just look at this real fast in the solution. All right, so there you go. There's position as a sine function. All right, last one, 66. 500 gram block, is that called 0.5 kilograms, released from rest, slides down a frictionless track. There's a 2-meter height drop, and there's a spring at the bottom. Find the maximum distance that the spring is compressed. Whenever you see like a maximum compression or stretch of a spring, that's a red flag that it's going to be what framework to solve it. Conservation of energy, right? We've got a height change, we've got a spring, there's another hint, it's probably going to be conservation of energy. Because what kind of energy at the very top? Gravitational potential, MGH, just do MGH, right? Okay. And then at the point of maximum spring compression, where did all the energy go? In the spring, that's called 1/2 kx squared, right? Okay, can you set those equal to each other and talk and stuff? Okay. Let me give you guys a weird question. See how they say that the surface is frictionless? Surface is frictionless, right? Right. So suppose there was no loss at all, so it collides with the spring and all the energy stays in the system. I got a what is in the system? What 3 objects are in the system? The block, the spring, and the earth. Block, spring, earth, right? We don't include the track because it's frictionless. Okay. Right. So is the spring gonna point, like bounce that block back? Okay? And if it was completely closed system, then how far up would the block go? All the way exactly to where it came from, right? Now that's an ideal situation, but that's like theoretically what it could approach, right? Okay, so good, boing, and back up to where it started. Okay, that's if there was no loss. All right, you guys good? You guys got a pretty good start there. All right, I'm gonna look up that one with the bananas. I thought I knew it. Oops, that's gonna be my homework. Yeah, we got a good head start. So we'll do some activities Friday, and then you guys know Tuesday we're gonna go over AP Classroom.